All right. Well, so I am pretty well known for having written Scala.js at this point. I'm still lead maintainer. This is mostly work I've done, I mean, over the course of many years. And even though I don't work at the Scala Center anymore, this was work I did while I was at the Scala Center, so giving them credit there. All right, so what are we looking at? Scala.js, the way it works, is first and foremost a language, right? Scala.js is not a compiler originally. It's a language dialect of Scala. And like Scala can talk to Java libraries, Scala.js can instead talk to JS libraries, right? And so there is a common ground, of course. Most of the language behaves the same, but there are specific interoperability features that are different in the both languages, right? In terms of architecture, the way this works is we start with some sources that have a .scala extension, and we send them to the Scala.js compiler, which is the Scala compiler augmented with a few more phases that generate SJS files. So these things here, they're special files that you can consider them as class files, except they follow our format. And just like class files know about Java semantics, the SJS files, they know about JS semantics, all right? And then this is what we publish in libraries, right? So on Maven, in jars, we push the SJS files. We don't have JS in the jars, okay? So when you, as an application developer, you depend on many libraries and you emit your Scala.js code, what happens is that you take your SJS file, but you also take the SJS files coming from all your dependencies. And then the Scala.js optimizer puts that in a big box, shuffles, outputs optimized IR that hopefully is fast and small. Okay? And then at the very end, there is a last thing that generates JavaScript code out of that. Okay? And what I'm presenting today is we're getting rid of that very last thing, right? And instead of generating JS code, we generate WebAssembly code and a little bit of JavaScript code to do the bridge, okay? So what is WebAssembly? Well, I'm not going to spend 10 slides talking about what it is. You can consider that it is JavaScript, but it's not JavaScript, right? It's another language that runs in your browser. Hopefully, through the talk, you will get a feel of what it looks like. What we ship is a binary, but there is a text format, and we will look at the text format, obviously. So in terms of coding effort and engineering effort, it's worth looking at the relative sizes of the various moving pieces of this whole architecture thing, right? So we have the compiler plugin for Scala 2 is around 9,000 lines of code. The equivalent code in the Scala 3 compiler is about 8,000. It's a little bit smaller because we made some changes inside Scala 3 to make Scala.js a little bit easier, but it's about the same scale, right? Then we have the linker and optimizer, which is shared across all Scala versions. That's a little bit more. It's like 14,000 lines of code. And then finally, so all of that we reuse, right? This is the same thing. It's the same code base between JS and WASM. There's no difference whatsoever. The thing that changes is that we have the JS backend or the WebAssembly backend at the very end that either emit JS or emit WebAssembly. And those are about 10,000 lines of code each, right? So the engineering effort for this work was about 10,000 lines of code to write. All of that is compiler code, right? And if we sum all of that up, we get this one, okay? So this is the sum of all the above. And that's not all that you see in the Scala.js architecture. There's more to it. There are a bunch of JDK classes that we have to implement, like Java long string or Java util array lists, that the rest of the ecosystem needs. So we implement them in Scala.js to compile them through this pipeline. And then we have a big test suite. So all of that, again, is all reused between those engineering efforts, right? It's the same JDK classes, it's the same test suite. We run the test suite on JS or on WASM, they behave the same. All right, so why do we care about WebAssembly? Well, first we cared because it's cool and we like writing compilers, but that's none of your concern, right? Why you should care is that we actually managed to make it faster than JS in many cases. So what do you see here? You see relative performance, so execution time, so lower is better, relative execution time compared to the JVM. So you actually see three things here. You see the JVM is always here at the 1 mark. Right? Everything above is slower than the JVM. Everything under is faster than the JVM. There is one here. Right? Okay, so the JVM is good. Right? It's really performant. And in blue, you see the JS backend, and in red, you see the WebAssembly backend. Okay? And up until here, WASM is faster. For some reason, we have ideas. We know some of the things. On the right of that line, WASM is actually slower than JavaScript. Right? So making WASM fast, I mean, WASM is not fast, okay? You have to make WASM fast. And we worked a lot to get there, and this is what I'm going to talk about in the rest of this talk, like all the things that we did so that we reached this point. In the beginning, the red bars were all up, right? They were above the blue bars, okay? So we worked very hard to get there. Yeah, so the geomean, so on average, the ratio WASM to JS is 70%, so a 30% improvement. And WASM corresponding with respect to the JVM is about twice slower, right? So twice as slow as the JVM, which has had like decades of optimizations into it, is not bad for the amount of like 2.5 people looking into these things, right? So and I think we can still make progress. So we're going to get good. All right, so let's dive into it. I need to show you a little bit of that SJS IR thing, the Scala.js intermediate representation, and I need to show you a little bit of WebAssembly, right? So here is some code, and if it's too small, move forward. Okay, so on the left, you have a Scala.js source code, okay? You have a main function, and you have one here, little compute result function that just computes a plus 2 times b. I splashed an @no inline on it so that the optimizer doesn't just inline that into the body of main, and then I cannot show you the function itself anymore. So it's got there, okay? And in the IR, this looks like this. So we have fully resolved method calls where the overloading semantics have been encoded into the names, right? But otherwise, we have primitive types, and we have result types. And then every operation is annotated with the type of elements that it's using, right? Nothing is left to chance anymore. Everything is well resolved, okay? The rest of the IR, don't bother too much, okay? So when we compile that to WebAssembly, we take the IR, which was optimized. Well, this one is still the original IR, and we generate this WebAssembly function here. So here you see that you still have this encoding of the overloading resolutions, and you have types. You have a parameter dis because well, WASM doesn't know what a method is. It only knows about functions. So the dis value is given as a parameter, which is a reference to main star. So WASM has references, right? GSeed references. And then we have a param A, which is an I32, and a param B, and it has a result, okay? And then there's something weird here because we're pushing A and B on the stack. So the way that WebAssembly works is like the JVM bad code. It uses a stack, at least in terms of spec, right? Not in terms of implementation. So it started with an empty stack. the first thing we do with a local get A is we put the value of A on the stack. Then local get B, we put the value of B on the stack. And then we push a constant 1 on the stack. And then we do an SHL, which is a shift left. So we pop 1, we pop B. So we remove those things. And instead, we write the result of computing B shift left 1. Okay? And then we do the same with the addition. So why shift left 1, whereas in the original IR, I had 2 times B? Well, that's because the Scala.js optimizer went this way, shaked it a little bit, and considered that instead of doing B times 2, it would be better to do B shift left 1. Right? Every optimizer in the world does that. Shifts are faster than multiplications. So, and shift by 1 is the same as multiplying by 2. Okay? All right. So here is the WebAssembly type system, at least what you need to know about it for today's talk. You have several types. You have primitive types, which are uninterpreted bit types, except they're interpreted as it's an integer or it's a floating point. But if it's an integer, we don't know whether it's signed or unsigned or whatever. And then we have reference types. And reference types point to a heap type. And the heap type has a hierarchy, which you see here in yellow. At the top, you have any, which is any reference. Then we have EQ, the references that you can compare for identity. You have arrays, you have structs, and you have the special I31 kind of thing, which is a 31-bit integer that you can put in a reference without boxing. And then inside structure, you're allowed to define your own. And that's the nice part, right? You're allowed to define your own structs that follow a subtyping hierarchy. And so we use that to encode our class hierarchy into the WebAssembly struct type system, all right? And then the reference types that are the types of values then follow the same hierarchy, okay? So you have 2 parallel hierarchies, the heap types, the reference types. It's not that important, but it's just the way it is. You have the definitions of the types, which are the heap types over there, and the reference types are the types you use, but it's not that important. All right. So now I need to talk to you about JavaScript interop. This is what Scala.js interop look like with JavaScript. This is Scala.js code, but unless you're quite familiar with Scala.js and with jQuery, you'll have a hard time figuring out what in that code is Scala and what is JavaScript. That's because it's all both, right? This is Scala code that talks to a JavaScript library, and this is perfectly fine, right? You can do that all the time. You can call the DOM here. You can use your own Scala things here, and then you can call methods of the canvas rendering context, which is a DOM thing, so you can call JS methods. You can pass them Scala values, which are going to get converted. Well, they're not converted, they're the same thing, but it's complicated, whatever. And then you can even call higher order JS methods, give them a Scala lambda, and they will know how to call that as a JS function, right? So it's very deeply integrated, right? And this is what I mean by the Scala.js language, right? This is not compiler features, it's not FFI, it's not foreign. In Scala.js, JS semantics are an integral part of our semantics, right? They're not foreign to us, they're really within the language. So let's look at how we compile that to a WebAssembly world, because WebAssembly doesn't have JS interop. WebAssembly has a very narrow set of things it can do to call into specifically imported functions, and it can do things. So how do we translate our language semantics into this new world of WebAssembly that cannot really directly talk to JS, right? So let's look first at our source code for the definition of the global console object in JS. So we annotated as this is a native object. It's in the global scope. It looks like this. It has a method def log that takes an any, returns a unit. Trust me, I know. Right? And then we have our compute result, which is in IR, in source here, which is going to console log the result of computing A plus B. Right? So A plus B is an int operation here happening on the Scala side, and console log that thing is a JS method call. In terms of IR, we get this thing here, where you see that the A plus B is really annotated as this is an int operation, this is an int addition, but the method call has a funny look in the IR. We get the global console object, and then we call the method string log on it, because in JavaScript, method names are strings that are reified at runtime, right? So fundamentally, this is what you do. You call a method, you actually give it a receiver, a method name, which happens to be a string, and then arguments. All right. So this is the same IR that we just saw, and this is the WebAssembly that we get out of that. So we can do this part here, which you may have gotten familiar with now, that I push A on the stack, I push B on the stack, I perform an addition. So now I have on my stack the result of the addition. But then I need to call console log. I don't have console log, I'm in WebAssembly, right? So what I do is I call this little helper here, which I have defined here as an imported function. Okay, so I import a function that from the module Scala.js custom helpers that has the name 2. And I declare that it takes an integer and it will return an anyref. Where is that function implemented? Well, remember from the very first slides, I said instead of generating just JS code, we're generating WASM and a little bit of JS. Right? That little bit of JS is this thing here. So this here is the little function, the little bit of JS that we are generating to do that. And this is the corresponding, so you see that it has the name 2. So this is the same 2 as here, right? And then the body is an arrow function that takes an x, and we'll call console log.x. What you can see that is actually a bit funny compared to the IR here, where log was a string literal, which is just one argument of this operation, which is a method call, right? And console, which is also just one argument of this method call operation, those two things, we embedded them directly into the JS helper. But the arguments, that one, we can't get it from JS. We have to pass it from WebAssembly, right? So the x, we added as an argument here, and we are parsing it here as an argument to the imported function, right? Why do we do that? Is that if we pushed all the arguments through the boundary every single time, including the method names as string literals going from WebAssembly into JS, the whole thing would be super slow. Right? And that is what we had in the beginning. That was super slow. So we push inside the JS helpers as many constants and global variables and method names as we can, so that we only have to pass through the boundary a limited amount of things. It's not really the passing the things. It's more that when the engine, the JS engine, then sees the console log here, it can optimize that much better than if it just sees call any receiver with any method that is a string that I will know at runtime that it cannot JIT optimize for, and with any arguments, right? So we do that for the benefit of the JIT to be able to optimize that method call so that it's not too slow. So this is one of the many things that we had to do to make this whole thing not terribly slow, okay? One fundamental consequence on boxing that this whole thing brings is let's go through it. So, okay, so we have this function here, which is a method that creates a JS array and puts 2 ints inside them, okay? And then I take that JS array and I give it as a constructor to int32 array, which is a typed array in JavaScript, and then I access the first element of that typed array. in terms of WebAssembly, what we get is that we're going to call a first helper to which we pass x and y. And that first helper will create an array of 2 elements, x and y. So this is a helper because it needs to create a JS array, right? So we need to ask JS, please make a JS array for me. And then we have to do this call new int 32 array. Again, this is instantiating a JavaScript class. We can't do that ourselves, so we ask another helper to do that for us, right? And finally, we access TA at index 0. And again, this is a JS-typed array indexing operation. We cannot do that from WASM, so we call a third helper that will access index 0 for us. Notice again that 0 is a constant that we tried to push very hard to the WebAssembly side, right? That's okay. So when we do that, and we have primitive ints that we pass. So the signature of the first helper takes primitive I32s, right? And the boundary, the way the spec works between WebAssembly and JavaScript will do the right thing. It will convert our I32 into a JavaScript number in the range of a signed 32-bit integer, which is exactly what we want. So here, everything's fine. No boxing shenanigans. The WASM.js boundary does the right thing for us. But what if I abstract this a little bit? And instead, I define my makeArray method, which is generic in its parameter t, and it takes 2 t's and it creates a JS array of the 2 t's. Then we have a problem because from this point of view, I have boxed things, so I have any refs. So the helper must take any refs as argument. And then when I call this method, what do I do? Well, I have an int, and I need an anyRef. The typical thing to do, and what the JVM does, for example, is that we box it, right? We put that in a box, a class, that holds the value inside one of its fields. Except if we do that, we have a big problem, because now I'm not passing a JS number to JavaScript. I'm passing an instance of my class. And JavaScript doesn't know about that. So it's going to put, it's going to put my instance of my class into the JS array. All fine. It's going to give me a JS array with my instance of my class. But then I try to put that into a typed array. And the typed array says, oh, I really wanted a JS number here. Like, I can't create an int32 array with your instance of your custom class. Like, that doesn't work, right? So I'm a bit stuck, right? What do I do? I can't use boxing. It's not possible. I have no control on that specific part. If we look at it in more details here, we start from here with an int or an I32. This is fine. And if we directly call in a monomorphic context, I have a primitive int, I give it to JS, I follow this arrow. And this arrow I have control over, right? First, I have the nice JS WASM boundary that does the right thing here. But if you need a little bit more control, you can customize this specific arrow, right? And but if you box, then you have some boxing and unboxing operation that you have control on as well. But once you are in the any ref world, and it flows into JS or back, then we have no choice whatsoever. We will get what the WASM to JS interrupt tells us that we will get. Except we have to make sure that whether you take the first arrow or whether you go this way, that you end up with the right thing, right? That you end up with the same thing. Worse, you could go all the way through different paths. Let me show you this more clearly. I prepared those arrows, I think. No, it's all broken. Yeah, whatever. So you could do the full circle, and you have to get back to where you started, right? And this is hard. And yeah, for the category theorist in the room, we basically want that diagram to commute. Right? So how do we do that? WASM cannot do that. JS cannot do that. In fact, when I presented the specific slides to WebAssembly people, like the people who make WebAssembly and its interop with JS, they were like, huh, you can do that? Yes, your spec says I can, and so I do. So what I do is I ask JavaScript for a little help with those two helpers, which are identity functions. How is an identity function helping? Well, because their signatures from WASM are not identities. Their signature of the first one is it takes an I32 and it returns an anyref. And the other one takes an anyref and returns an I32. And it works. The spec says it works, and it works. I can take an I32, maybe I'll let me scrap a little bit all these things here. Right? I can take an I32, I can box it with that identity function that returns me an anyref, but it's an anyref that holds a JS number, so I'm all good. And then the WebAssembly interface will turn that JS number inside an anyref into a JS number, and I get my JS number. And if I need to unbox, I go the other way, right? It's the other way around. So this time I take an anyref as an argument, and I return an I32 in the other direction. Okay? So this works. It has the right semantics. It's atrociously slow. So instead, we try to be a bit smarter, especially for ints. And so this is IR. This is the unoptimized method WebAssembly call that would be interesting. But what is interesting is those calls to BI here and UI for boxint and unboxint. And boxint here is starting by trying to see if the last bit is really all that important. Like, can we throw away the last bits? If we can't, if it is important, then we are going to call the JS helper, which actually goes to the JS boundary and back to give us an anyref. But if the last bit, so the higher orders bit, right? If that one is not all that important, then instead I'm going to use the WASM magic ref I31 thing here. So I'm going to put a 31-bit integer into an anyref directly from the WebAssembly code. And it turns out that the spec is nice to us. It says that if I have an I31 ref, on the JS side, it's going to be seen as a JS number in the right range. More importantly, it goes the other way around. If I start with a JS number that happens to fit in exactly the right range, on the WebAssembly side, I'm going to get an I31 ref, and so I can unbox it without leaving the WebAssembly world, so it stays fast. So this way, boxing and unboxing of integers is fast most of the time. It's only slow if your higher order bit is actually important. And if you think about it, think about your programs. Think when was the last time that you boxed an integer for which the highest order bit was actually important? My guess is never happened. So it's fast. But we would like it to work for that last bit as well, and we would like it to work for booleans and for doubles and all the other ones, right? So for that, I started a new proposal to WebAssembly called a JS primitive built-ins proposal, which will give those helpers as built-ins that then the WebAssembly VM can optimize all the way through and never leave the WebAssembly world, but give me a proper JS number or JS Boolean without any overhead, right? That proposal passed the first stage of the process. So they are actually willing to improve WebAssembly for us, right? The JVM never cares about Scala, right? Where there's this tiny little thing there. Oh yeah, hey, hi Scala. Oh, you don't like what we're doing with the JVM? Ah, tough luck, right? But WebAssembly, they care. right? You can actually get into this world of specifying and improving WebAssembly and get them to add something that is going to be useful for Scala, right? This is absolutely awesome. All right, I'm going to go just mention another thing. One thing that doesn't work, right? @JS export. So in Scala.js, you can annotate a method of a Scala class with @JS export, and then JS can call that method, assuming it receives an instance of that Scala class somehow. You can not to be confused with import and @JS export top level, which are actually more related. These are module imports, module exports, those work. Here I'm talking about exporting a member of a Scala class so that JS can use it. So @JS export. That is not possible to implement today in WebAssembly JS. It's just not possible unless you compile all your Scala classes to JS classes and then you cross the bridge every time you want to access a field or call a method, which is completely stupid. So given that you want to compile your Scala classes to WebAssembly structs in the first place, which we want to do, it is not possible to expose that. So that doesn't work. It's silently ignored by the WebAssembly backend after the Scala.js optimizer has done its thing. But there is hope. There is another proposal, which was not by me, but I'm actively involved into shaping it the right way, which is custom descriptors and JS interop for structs proposal. And that will give us exactly the necessary tools. It will allow us to attach JS prototypes to WASM structs. It will give us exactly the tools we need to be able to implement our @JS export. So the last thing we cannot implement, give it a year or two, and we will be able to implement it. So I'll quickly finish with one of two things I had planned to, but looks like I'm only going to give you one, where for the most part, the way we had designed our IR was good already to compile to WebAssembly and make it fast. But there were two things where we had made mistakes, like 8 years ago, that prevented us from producing fast WebAssembly today. And we fixed those. The first is closures. If you write this code in Scala.js before 1.19, this is Scala, right? You can take that code. It works on Scala JVM as well, right? Nothing JS specific about that thing. But if you compile it with JS, the IR you got was this thing, where we instantiate a unique add-on function 1 class that takes as an argument to its constructor a JS lambda that does the thing. So this arrow lambda here is a JS closure in our IR that takes an any, returns an any, unboxes, computes, and boxes at the end, right? This is good in JS because it means we only have one class implementing all the functions in the world, so no code size bloat, right? This is good for code size. It's also very performant because, of course, JS is good at doing a JS closure. But WASM doesn't like that at all. Yeah, this is the... so this is what you end up with in the JS code, right? So you end up instantiating that one class, and you pass it a JS closure. This is the JS code that gets generated. On WASM, we cannot create a JS closure from WASM. So what happens? Well, we ask a helper to do it for us. Well, same good old story. We ask a helper to which we give a WASM function reference and some closure data, captured variables, and it returns a JS closure that will call that function. So imagine what happens when you call that function from WebAssembly. You go through the boundary twice. You're giving that in a map. So you're crossing the boundary twice for every element in your list. That is atrocious. Right? 10x slowdown here. So this is absolutely terrible in WASM. So since 1.19, Scala.js, the compiler generates new IR we added new capabilities to our IR to represent an abstract notion of a lambda that has a superclass and has a body which is typed. And then the JS code can choose to emit a JS closure, and the WASM code can choose to emit a struct with a function reference and stay entirely inside. So in JS, you end up with exactly the same thing, except that the one class that implements it has got a funny name, but there is only one in the entire world, so it's still fine for code size purposes. And in WASM, I won't go through it, but the one thing you can see is that there's no JS helper anymore, so it's all great, and it's also fast. So that took significant effort, especially to make it compatible with what we had before. So we have hacks when we read IR from previous versions to patch it up to work in the new system so that even libraries built with previous versions of Scala.js are going to be fast in WASM today, which is, that was tricky to do, but we did it. The other thing I'm not going to cover, but you can ask me later, is var args. It turns out we did something similar with var args. We put them in a JS array, and we embed the JS array instead of having a WASM array. So this is slow. I'm not going to go over it, but you can ask me later. I'm happy to answer questions. So fixing that is still under review. There's a PR open, but it's still under review. So it will probably ship in 120. It's not yet there. So the benchmarks you saw are for that PR branch. All right, that brings me to basically the end. We also had to change a little bit our JDK implementations. We have some ifs and else's to implement some things a little bit differently, but nothing really important like JS array lists, for example. In JS, there's a JS array inside because a JS array is growable and shrinkable. But on WASM, we implement it differently now. And I'll just mention this one. Something I really like, async await support has landed in Scala.js 1.19 for JS. And so you can create a JS async block, and you can await in it, right? And then the other thing just promises and returns a JS promise. You can do that in JavaScript. You can do an async await block, but the await has to be inside the async, right? If you try to put the awaits here, return a string here, and have only a JS async here, that's no, right? The compiler tells you cannot put the await outside the scope of the JS async, including inside the higher function, right? But in Scala.js WASM today, you can. And this is JSPI. And so you can have arbitrary number of call stacks elements between one JS async, go down the stack, call many methods, and deep inside do an await. It suspends the stack. It's fast. It's like Loom, but on WASM.js. It's great. This is the technology that Gears uses when compiling to Scala.js WASM. You should try it. It simplified my personal project. Like, it's amazing. I got no futures, no promises anywhere. Just one async at the start, what awaits inside. Awesome. Like, this is a new superpower that we get. JS doesn't have, WASM doesn't have. WASM and JS together have that superpower. Absolutely awesome. And with that, I'm done. So I'm happy to maybe take one or two questions. Technically, the slot is over, but
yeah, I think we are out of time. So maybe you will be available, Sébastien, after the talk, during the break or during the lunch to take the questions. Is it okay?
Yeah, sure.
Okay, let's thank Sébastien for his work. Yeah.